Hello everybody, I am Nini Mathews. Would like to thank the organizers for this opportunity. In today's presentation, we'll be discussing the development of chalcogenide thin films by electrodeposition. I work for the Institute of Renewable Energy affiliated to National University of Mexico. As an outline of the presentation, an introduction about the solar cells, current status of the thin film solar cells, cadmium telluride, cadmium zinc tin sulfide, thin film deposition by electrodeposition, taking examples of antimony sulfide, selenide and sulfoselenide, characterization of these films, and heterostructure cadmium sulfide, antimony sulfoselenide. It's a schematic of a traditional PN junction solar cells. Both substrate and superstrate configuration as shown. This is in a PN junction solar cell, the light enters through the N side. The electron holes are produced. The internal field separates the electron hole pairs. The electrons move towards the N side, holes moves towards the P side. These are efficiencies of the present leading solar cells. Cadmium telluride in the 22.1 and copper indium gallium selenide around 23.5 and copper zinc tin sulfide around 12.6%. In our group, we work on the development of binary, ternary and quaternary semiconductor materials. Today I'll be presenting the results on sulfides and selenides of antimony. These materials are important because mainly of their abundance in the Earth's crust. The availability of these materials compared to the tellurium and indium is much more, which is an important criteria that has to be considered while developing the solar cells. They are relatively non-toxic and many different low-cost preparation techniques are available for the development of these materials. It is very important to note that their optical and electrical properties are in the range of par with cadmium telluride and copper indium gallium sulfide. Antimony sulfoselenide has demonstrated an efficiency of 10% by hydrothermal method. The efficiencies of these materials are still in this range. There are much more room to improve. Their theoretical efficiencies are close to 30%. I'd like to start with the electrodeposition process. Here I am presenting a schematic of a 3-electrode cell. This is the reference electrode, the working electrode, and the counter electrode. The voltage is measured between the working and the reference current between the counter and the working electrode. In an electrodeposition process, the ions in the solution, there is a charge transfer on the electrode surface, get reduced and deposited on this conducting substrate. Here shows an image which is close to what is happening on the electrode surface. There are many ions close to the ions in the solutions are like hydrated, moving around in the solution. These hydrated metal ions in the solution migrate to the cathode by diffusion due to the concentration gradient or the electric field applied and the convection current. Through different mechanisms they reach the electrode surface. Once these electrodes reach the electrode surface, this hydrate envelope is lost and the dehydrated ion is neutralized by the charge transfer and get absorbed on the cathode surface. That is a process that is happening during the electrodeposition. There are many factors that are influencing the process, like the current density or the nature of nature of the cations and the anions that we are using, and also the power supply or the power supply current waveform. Electrodeposition can be done using applying various electrochemical techniques. It can be using a constant waveform or through a dynamic waveform. In the case of a constant waveform, can be by a constant current or a constant potential, or if it is a dynamic, it can be given like pulses, like pulsed deposition, or like a cyclic voltammetry, changing the voltages. Different techniques can be used. So now with the antimony sulfide will be explained using the process of will be deposited by pulse electrodeposition, whereas antimony sulfide through constant potential electrodeposition, and antimony sulfoselenide also through constant electrodeposition. These are the cathodic reaction. Here I am showing a cathodic reactions involved in the case of an antimony sulfide. For the deposition of antimony sulfide, the precursors are antimony as well as there should be a sulfur source. Here we used antimony chloride and thiosulfide. So the reduction of antimony on the cathode surface, there occurs the reduction of the antimony and the reduction of thiosulfate to sulfur. This standard potentials of antimony as well as the thiosulfide. For the co-deposition, the potential of these two elements should be brought together so that both of these elements deposit. To start with the deposition, the potential of each element should be checked with the cyclic voltammetry. This gives the cyclic scans in 3 solutions like antimony chloride, thiosulfide, and the mixture of the both. In this scan you can see that this started and the current is increasing, and on the reverse scan the current is there is an increase in the anodic current. This the increase in the cathodic current is due to the deposition of the antimony, and this stripping current is due to the dissolution or the oxidation of the metallic antimony. This current much farther is due to the hydrogen reduction. In the case for the thiosulfate, there is however an oxidation peak may be absent due to the reduction of sulfur to hydrogen sulfide. This part, the thiosulfide might have reduced to sulfur. In this case, we are not observing an anodic peak, maybe because during the process, this sulfur might have further reduced to hydrogen sulfide. This is a cyclic voltammetry in a solution containing both the solutions. We can note that the reduction potential have pushed to higher negative potentials. Here it was 0.38 and this was little more pushed to higher potentials. And so we know that in this region we can deposit the antimony sulfide. We deposited antimony sulfide using pulse electrodeposition. The electrolyte was with the antimony chloride and thiosulfate. The potential pulses applied was like 0.72 and plus 1 volts. Can see that in this case, this is the potential, real potential pulses. That is the current and the time while during the electrodeposition. This is during the deposition and this is during the dissolution. During this stage, where the dissolution stage, the weak bonds of antimony sulfide or the excess of any antimony that is there can be removed. Thereby we can develop more uniform and stoichiometric films. These are the results of antimony sulfide developed by pulse electrodeposition. The study shows that The as deposited films were amorphous. However, when it was heated, there was all the peaks of antimony sulfide appeared, and it is well coinciding with the powder diffraction patterns of antimony sulfide. AFM images shows a grain-like structure morphology, which has been the similar like can be seen in the TEM images also. This thin films of antimony sulfide, selenide was developed by constant potential. Here the CVs of different scan rates are shown. It is all has a similar shape. This shape indicates that it is like the process. All the scans have the similar current, and in this case, the sweep speed changes the value of the current density. The shape is the same, but the current density is changed. The size of the diffusion layer depends on the voltage of the sweep speed. For slow sweep, the diffusion layer will be larger. Therefore, the current higher at larger scan speeds. Here, the plot shows the plot of peak current density with square root of velocity scan rates. The linear plot shows that the process is controlled by nucleation and diffusion. This figure shows the initial stages of the chronoamperometric curves of the deposition. This curve gives an idea about the type of nucleation and growth. There are these IT curves of sp2 are at different potential but have the similar form. The region on the curve A these regions on the curve can be divided, like can be seen this region as A and this region as B. An increase in the current density associated with the nucleation process followed by a diffusion controlled process. Here an increase and followed by a diffusion control, but here a saturation growth, a region where the current density is constant, indicating a saturation growth. The nucleation mechanism can be identified from this graph, from this curve. For the nucleation of the 3D instantaneous nucleation and the 3D progressive nucleation are given by these equations. And in our case, we can see that our process is more close to 3D instantaneous nucleation. This shows the XRD figures of the films deposited at different bath concentration. The possible impurity phases like antimony and the oxide of antimony are also included in the film. In this one, you can see that there are no impurities. All the peaks correspond to the antimony selenide. However, when we did the Raman, we saw a shift towards a lower lower side. This can be associated with the change in the composition. You can see that the films deposited at 0.7 selenium to antimony precursor bath had the ideal composition. Here shows the band gap of the films. You can see that the band gap is decreasing with the increase in the bath concentration or increase in the selenium in the bath. As expected, the selenium incorporation is higher, and which results in a decrease in the band gap. This is films annealed is the stoichiometric film annealed at different temperatures. We can see that the films annealed at 325, 375 and 425, these films showed a better morphology or a better crystallization. We discarded the film at 475 since when there is the formation of a new phase, which was on this, and so the optimized annealing temperature is between 325 to 425. This shows the photoelectrochemical measurement of the antimony sulfide or antimony selenide films. You can see that the increase in the cathodic current. The films were the photoelectrochemical measurements were done for all the films annealed at 3 different temperatures. There is an increase in cathodic current under the illumination, showing the conductivity is p-type, and see that the injected carriers are electrons, confirming the p-type conductivity of the material. Here I will show the excited results of the antimony selenide films, antimony sulfoselenide films. Taking this region, we can see that the peak, as the antimony concentration is increased, the peaks are shifted towards the lower region and towards the lower band gap, a lower region. Here this is the potent deposited at 0.6, and then it is at 0.66 and 0.72 volt. Then there is the incorporation of antimony. The incorporation of has caused the shift towards the lower 2 theta values. The lattice parameters of these were calculated and was in between this antimony selenide and sulfide. The band gap of this material was also estimated. You can see that the band gap of this is the band gap of antimony sulfide, and this is the band gap of antimony selenide, and this band gap of this material were in between the band gap of these two materials. The photoelectrochemical measurements showed that the materials are p-type. The negative slope shows that the materials were p-type, and the band edges calculated from the flat band potential, it showed that the electron transfer is possible. We developed a solar cell based on this material, which has to be further improved, but then reached a sufficiency of here the cadmium sulfide is deposited by chemical bath method, and antimony sulfoselenide by chemical bath. And in this case, the efficiency of the efficiency we received was up to 1.7%, which needs, of course, further improvement. Here, the antimony, as a conclusion, the antimony sulfide films were deposited by pulse electrodeposition, antimony selenide by constant potential electrodeposition, and antimony sulfoselenides by a one-step electrodeposition process. Antimony selenide based photocathodes and antimony sulfoselenide cell were demonstrated. I would like to acknowledge the students and the collaborators for this work, and acknowledge the financial support received. Thank you.